Tuwan, certified personal trainer, food nutritionist specialist, and creator of Intelligent Fitness Design, the boot camp for body and brain, the fitness program where the brain is a muscle too. Today, IFD is on a field trip, an educational expedition. We're here at the Public Museum in Grand Rapids, Michigan, to view a very forward-thinking and exciting exhibit. Well, I think it's exciting, but I'm a nerd, and that I love museums. And anytime that I have the opportunity to go out and explore one and empower myself with knowledge and education, I do so. So let's get it. So here we are at this amazing exhibit called Brain, the world inside your head, where they have successfully combined knowledge and education with technology and imagination to help us learn and better understand and observe the processes and functions that go on in the brain. Today's fitness zeitgeist is motivated and inspired by cognitive skill building, activation, and strengthening. And IFD hopes to be at the forefront of that fitness zeitgeist. Brain training involves cognitive skill building and strengthening through the use of brain games, such as word searches, Sudoku puzzles, memory cards, even the Rubik's Cube. Cognitive activity, such as reading and studying, will greatly improve and enhance cognitive skills such as learning, memory, and comprehension throughout the course of your life if done consistently. Today's research indicates that multidimensional lifestyle changes are greatly enhancing and improving both body and brain health. Brain training, together with other activities such as physical fitness, proper nutrition, including brain-healthy diets, and social engagement, are all activities that we can participate in our lives to help us live more healthier, productive, and active years as we age. Today's research reveals to us that what's good for the heart is good for the head, and what's good for the head is good for the heart. So what is good for the heart? Cardiovascular training is great for the heart. Of all the forms of training, cardiovascular training helps to prevent more chronic diseases than any other. It helps to prevent hypertension, diabetes, obesity, and coronary heart disease, the leading cause of death in Americans today. The American Heart Association suggests that we should get in 150 minutes of cardiovascular training in a week. Quickly, I want to discuss with you in more detail something about cardiovascular training, the different forms of cardiovascular training. Cardiovascular training is any form of training such as walking, running, swimming, and biking, and especially circuit training that strengthens the heart and the cardiovascular system as a whole and helps it to work more effectively and more efficiently. I want to speak specifically about circuit training. Circuit training is an awesome form of cardiovascular training, specifically as it relates to Intelligent Fitness Design, the boot camp for body and brain. However, circuit training is a very forward-thinking and unique program. With IFD, circuit training is a form of training where you go from one exercise to another in succession. And in between the exercises in the circuits, there is a short timed rest interval. In that rest interval, IFD has placed brain games, word searches, Sudoku puzzles, memory cards, even the Rubik's Cube, and a plethora of other brain games to help build cognitive skills, thereby working both body and brain. So, in IFD's effort, or Intelligent Fitness Design's effort, to always strive to bring you new, innovative, forward-thinking ways to elevate your workouts to a higher level, we're going to engage in an experiment today, a sociological experiment of sorts. We're going to take the normal curriculum of the IFD program and we're going to substitute it for the brain activity, the reading and study of the brain exhibit. So what we're going to do we're going to do a couple of exercises. We're going to do a dynamic stretch followed by a plyometric stretch, followed by a plyometric exercise, and then from there we're going to read the brain exhibit, and then we're going to do another 2 exercises, and then we're going to read another brain exhibit, thereby working body and brain. And we're going to call this Intelligent Fitness Design, the boot camp for body and brain, inspired museum workouts. If you can have mall walk, why can't you have museum walk workouts? So let's get it. So here we are at the first station to do the first exercises. We're going to do a basic dynamic stretch, superset it with a plyometric exercise. We're going to do a squat. We're going to superset that with a squat with stabilization. All right, here we go. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now squat jumps with stabilization. 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. 4. 1, 2, 3. 5. 1, 2, 3. 6. 1, 2, 3. 7. 1, 2, 3. 8. 1, 2, 3. 9. 1, 2, 3. 10. Good. Now on to the cognitive activity, lightning storm. Your brain lets you see, hear, smell, taste, move, think, feel, and care. It allows you to walk and talk, learn and remember. Your brain processes your thoughts, moods, and emotions. It makes you conscious and keeps you alive. Everything you do and everything you are comes from your brain. And everything your brain does comes from electrical signals and chemical connections. At its core, your brain is a lightning storm. Gobs of gap. Neurons are busy and unbelievably crowded. A neuron may receive messages from 100,000 other neurons, each one arriving 1,000 times every second. A neuron may have 100,000 synapses, each swarming with hundreds of thousands of neurotransmitters. This tidal wave of messages keeps the lightning storm going. So they have made a facsimile of how neurons fire. Launch an electrical signal along the neuron. At the end of the neuron's long arm, the signal will arrive at the synapse gap. There it will dispatch neurotransmitter molecules to carry the messages to the next neuron. The transmitters are waiting. They can't pop across the synapse without the signal. So here we are at the second fit brain station. We're going to do a sagittal lunge with reach along with a plyometric exercise, the jump lunge. All right, so here we go. 1, 1, 2, 2, 3, 3, 4, 4, 5, jump lunges. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. From physical activity to cognitive brain activity. Now on to cognitive activity or brain activity. Fetal development. Wiring in the womb. You begin making neurons and wiring them together in your mother's womb. Your brain grew fastest during these 9 months of gestation, gaining about 250,000 new neurons every minute. But they were not yet completely wired together. That happened as you experience life in the world. Who are you? When do you learn who you are? Until 18 to 24 months of age, babies usually don't recognize themselves in the mirror. Neurons in their brains, especially in the frontal lobes, haven't yet made the necessary connections. Until then, infants may look in a mirror and think they're seeing other children. Birth to age 2, infant connections. While you're born with almost all the neurons your brain will ever have, many neurons aren't yet wired together. Now, as an infant begins to experience the sights and sounds and sensations of the world, neurons fire. Every time they fire, they build connections with other neurons. Neurons that fire together, wire together. Use it or lose it. At first, following your genetic blueprint, your brain makes more neurons and connections than you'll ever need. Then your brain starts to prune out those you don't use. That's why a variety of experience is so important for children. Early experience designs your wiring just right for you. Sorting sounds. While much of an infant's brain isn't yet wired, the sound areas are already developed at birth. Babies can distinguish all sounds of every known language, but if you grow up hearing only your own language, your brain strengthens those circuits and lets the others go. By the end of the first year, it's harder to recognize differences between sounds in other languages. Your babbling brain, da 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 da, ba 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 ba, ma 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 ma. Why do babies babble? As practice for talking, but not just for talking out loud. Deaf babies exposed to sign language also babble with their hands. Your brain seems to have a built-in ability to understand and speak language, no matter what kind. Babbling with your voice or your hands represents baby steps in that process. Childhood fine-tuning. By the age of 2, your brain has twice as many synapses and use twice as much of your body's energy as an adult's brain. Now your brain begins to fine-tune itself, strengthening connections you use and pruning away connections you don't. Your wiring is starting to become permanent. Yakety yak. Now is when you learn to speak and understand language. During your early childhood years, neurons in your brain's language regions wire themselves into a thick tangle of interconnections. After this spurt, by age 6, learning new languages becomes harder. Adults can still learn languages, but most will never master them as well as children can. Brain bites. By age 4, your brain has grown to its full size. By age 5, your brain has gained almost its full weight. Your childhood years are the best time to develop strong math, logic, and musical skills. During your childhood years, your brain can rewire itself to make up for many injuries. Ring a rod. Adolescence, finishing touches. During your teen years, your brain puts finishing touches on its wiring. Some abilities, learning a new language or playing a musical instrument, become harder to master from now on. But others, such as gaining insight and judgment, dealing with emotions, and planning, blossom. Less is more. These finishing touches involve pruning your brain's wiring as much as making new connections. During your teen years, your brain cuts away unnecessary wiring, making your neural circuits stronger and more efficient. Your brain is maturing and preparing you for adult life. Adulthood peak condition. In adulthood, you enjoy the full force of your thinking powers. Although you will be able to learn for the rest of your life, your brain's circuitry is almost set. Your life experiences have modified your genetic blueprint to custom wire your brain. Your brain is now mature. Your changing brain. A mature brain doesn't mean a static brain. In adulthood, your brain continues to change. For example, from now on, thousands of brain cells die every day. Beginning around the age of 20, your brain loses about 1 gram, 0.004 ounces of weight every year. But the remaining neurons strengthen existing connections and form new ones. That's how you keep learning. Brain changes in space. Experiments aboard NASA's Neuralab mission suggest that the adult brain can change to adapt to the near weightlessness of space. In onboard laboratory rats, areas in the cerebellum that receive input from gravity sensors in the ear show changes similar to the pruning of connections during development. Aging, coping with less. As your brain ages, it slows down. More neurons degenerate and die, and they produce fewer neurotransmitters. Not only does your ability to learn new things fall off, but your senses and physical skills decline. But aging can also bring advantages. The experience of living can help you solve problems and gain valuable insights. Use it or lose it. In old age, your brain still responds to stimulation. For example, after the age of 60, your brain generates a special type of glial cell that encourages new circuits to form. These support cells may help your brain compensate for the losses of aging. Your brain can remain dynamic throughout your entire life. So here we are at the third brain fit station, and the exercises that we're going to do is the frontal lunge with reach and jumping jacks. All right, so let's go. 1, 2, 3, 4, 5. Now jumping jacks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. From physical activity to brain activity. Mapping the mind. In the 18th century, many people thought that everything the brain did involved the entire brain. Then scientists began discovering what we know today. Different parts of the brain have different functions. These were beginning attempts to map the mind. A hole in the head. In 1848, an explosion rocketed an iron rod into the cheek of a 25-year-old Vermont railroad worker named Phineas Gage. The rod passed through his brain and out of the top of his skull. Gage collapsed onto the ground. Yet moments later, he sat up and began to talk. The accident destroyed a chunk of his brain, leaving a hole in his head. Gage lived for 12 more years, but something vital had changed: his personality. The place of personality. Before his accident, Phineas Gage was kind and cheerful, a hard worker and a loyal friend. After his accident, he became lazy and quarrelsome. Gage said his friends was no longer Gage. His Dr. John Harlow suspected that the change in Gage's personality had been caused by the damage to the frontal lobes of his brain. Here was a clue that certain parts of the brain control certain kinds of behavior. A hole in the head revisited. In the early 1990s, a University of Iowa team led by Dr. Hanna and Antonio Damasio decided to find out what caused Gage's personality changes. By examining Gage's skull, they performed a virtual autopsy. When they compared the results to patients with similar personality changes, they discovered similar brain damage. John Harlow had been right. The frontal lobes are involved in rational decision-making and emotion. Bumps on the head. In the late 18th century, an Austrian, Franz Gall, thought that the brain was divided into sections that play different roles. He was right, but Gall also believed that the shape and size of the skull and bumps on its surface reveal your personality. He was wrong. Nevertheless, Gall's approach became popular. It's called phrenology, the study of the mind. Brain talk. Many brain discoveries have come from examining injuries. In 1861, a French surgeon named Paul Broca had a patient who could speak only one sound, tan. When the man died, Broca studied his brain and discovered a damaged spot on the frontal side, on the front left side. He suspected that this area controlled speaking ability. He was right. Broca's area was the first recognized link between a particular ability and a region of the brain. So here we are at the fourth Brain Fit station. We're going to do transverse plane lunges with a reach and burpees. Ready? Here we go. 1, 2, 3, 4, and 5. Other side. 1, 4, step reach in, 5, good. Now for burpees. Ready, set, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Good. From physical activity to brain activity. Searching for the mind. Our awareness of the brain has grown slowly over centuries. From the beginnings of history, people have searched for the location of thought, perception, feelings, memory, consciousness. People have searched for the mind. Historic notions. The ancient Greeks debated whether the brain or the heart was the seat of the mind. In the 2nd century AD, the Greco-Roman physician Galen thought that cerebrospinal fluid which bathes the brain and collects in the hollows called ventricles, was the essence of the mind. In Shakespeare's 16th century England, people thought the liver, not the brain, was the seat of emotion. I think, therefore I am. In the 17th century, the French philosopher René Descartes claimed that the mind exists apart from the body. He thought that the mind enters through a tiny gland at the base of the brain called the pineal gland. Today, we know that the pineal gland has nothing to do with the mind. It's involved in sleep and wakefulness, but the notion of the separation between mind and body hangs on. It's called dualism. A hole in the head. We humans have been making holes in our skulls for at least 5,000 years. The process is called trephination. Why? In Peru, at least, it was done to treat skull injuries. In other areas, it may have been to relieve pain and perhaps deal with psychological problems. No matter the reason, these holes in the head are a clue that early in our history we recognize the importance of the brain in how we act, who we are. And here we are at the 5th Brain Fit Station. We're going to do medicine ball rotations, superset and push-ups. All right, let's go. Good. Now for push-ups. Good. From physical activity to brain activity. Discovering the building blocks. In the 19th century, scientists still had no idea what the brain was made of. Then, in an Italian kitchen in 1872, a young doctor named Camillo Golgi accidentally locked a piece of brain tissue into a dish containing the chemical silver nitrate. When he looked at the tissue under a microscope, he saw dark blobs and stringy tangles. They were neurons. Golgi had stumbled upon a way to make the building blocks of the brain visible. Ramon E. Cajol's drawing of the spinal column illustrating the differences between Golgi's tangled net neuron theory, figure 1, and Cajol's discovery of gap synapses between neurons, figure 2. Understanding the building blocks. How do neurons work? Golgi and others thought that all neurons were connected to one another, like a tangled net. But in 1889, a Spaniard named Santiago Román y Cajol discovered gaps, synapses, between neurons. Each neuron was an independent unit. To communicate, a neuron's message would have to bridge the gap. Unhinge a brain. Our brain reflects its evolutionary stages. Cortex, an area of thinking. the distinguishing feature of the modern human brain. Limbic system, an area of memory and emotion, reflecting the old mammal brain. Cerebellum and brainstem, areas of autonomic functions and basic movement, reflecting the reptile brain. Let's see what happens when we do this. Look at that. Wow. You are who you've been. Brain evolution. Reptile brain. Reptiles living about 300 million years ago had brains primarily responsible for instinct, movement, and basic functions such as smell, sight, and respiration. Their brain parts are still reflected in our brain, in the cerebellum and brainstem, the areas of our autonomic functions and basic movement. Past and present. Present is past. According to the theory of evolution, our brain reflects the story of its past and its structure. Old mammal brain. About 200 million years ago, mammals developed brains that added memory and emotional behavior to their reptilian characteristics. In our brains, these qualities correspond to a group of structures in the middle of the brain known as the limbic system. This is the headquarters for our memory and emotions. Modern human brain. About 1.5 million years ago, the brains of our human ancestors began to grow explosively. They grew outward in layers as the cerebrum and its wrinkled cortex began to surround the older parts of our brain. This growth spurt pushed out the bones of our skull, creating our high forehead and domed head. These areas control thinking and language. The all-in-one, the evolutionary steps that formed our brain are still with us. We depend on our autonomic system, our ability to move, our memory and emotions, and thinking and communicating. Our brain needs all its parts. All are right. Our brain allows us to survive in our surroundings. The brains of other animals allow them to survive in their surroundings. Each animal's brain enables it to live in its own world. Slicing the brain. Brain sections have been prepared for over a century. Scientists soak brains in a hardening solution, then cut paper-thin slices with a microtome, a machine that resembles a deli slicer. The resulting sections reveal the brain structure. We've learned more about the brain in the last few decades than in all the years before. Why? Because of imaging and other modern scientific techniques. No longer must scientists cut apart dead brains to examine their structure. Now we can peer into living brains to see what they look like and how they work. Now we can examine brains live. MRI, magnetic resonance imaging, was first used to image the brain in the late 1970s. MRI employs powerful magnets and radio waves to pinpoint the location of atoms in the brain. Computers convert the information into sharper snapshots than CAT without exposing patients to X-rays by measuring blood flow. A type of MRI called fMRI, functional MRI, can show how the brain works during specific activities. PET, or PET, positron emission tomography, also was introduced in the late 1970s. It too shows the brain in action. It tracks down hard-working parts of the brain, primarily by detecting which areas receive the most blood. To do a PET scan, scientists inject safe but detectable amounts of radioactive chemicals into a person's bloodstream. The path of the radiation is then detected by special sensors, one on each side of the head. Computers use these signals to paint pictures of the brain at work.